Good morning, student. Let us start the session of 10 a.m. and the topic in this hour are Henry Law and Raoult's Law. Let us consider Henry Law first. It's a statement. It states that at constant temperature, the mass of the gas dissolved in unit volume of the solvent is directly proportional to pressure of gas above the surface of solvent in equilibrium with the solution. Try to understand by read it as much as time you possible, or you can also say that the partial pressure of a gas in vapor phase is proportional to the mole fraction of the gas in the solution. I hope you understand. You know that carbon dioxide gas is soluble in water, oxygen gas is soluble in water, nitrogen gas is soluble in water. The solubility of all the gases are different depending upon the nature of the gas. If the gas is polar, its critical temperature is low, then the gas is more soluble in water. So that is the solubility of gas in liquid. Mathematically it can be expressed as P, that is pressure that is the above the surface of liquid. That pressure is directly proportional to the solubility of gas. Means higher the pressure of the gas above the surface of liquid, the more is the gas soluble in liquid. It means that pressure is directly proportional to the solubility, and when you remove the proportionality sign, then you get P is equals to KH into X. X is the solubility. KH is a constant that is called the Henry constant, and KH depends on nature of gas. Its value is inversely proportional to solubility of gas, and its value increases with increase in temperature. Clear? It means that a gas which has higher value of KH will be less soluble in water. Suppose two liquid A and B has value KH 2 and 5. Then the gas which has value 2 is more soluble in water. There are some limitations of this law. Learn these limitations. This law fails. Limitations means कमियाँ. इस नियम की कुछ कमियाँ हैं. ये नियम कुछ समय फेल हो जाता है जब pressure is high, temperature is low, gas is highly soluble, and the gas reacts with the solvent and associate or dissociate in the solvent. For example, ammonia gas, you know it is highly soluble in water. So in case of ammonia dissolution in water, this law fails. Some of the gas makes bond with the water molecule. In that situation, the law will not applicable. Okay, now we come to the topic application, means where this law is applied practically. First is CO2 dissolved in beverage at high pressure. You know the cold drinks, when they are opened, then CO2 gas evolved come outside with a fizzy sound. That is the CO2 gas dissolved in excess pressure. Similarly, in case of sea divers, they carry cylinder, and that cylinder has helium along with the oxygen and nitrogen. Because helium is less soluble in our blood, so it causes less painful when you come outside the sea. The third application, at high altitudes, O2 dissolves less in blood and cause anoxia. The fourth is aquatic species are more comfortable in cold water than warm water, because cold water has low temperature, it has more solubility of oxygen gas, and the aquatic animals get more amount of oxygen. I hope all of you understand the Henry law. Read it again by stopping the sound. Let's consider the next slide. That is also an important topic, vapor pressure. Vapor pressure, that is a property of a liquid. It is defined as the pressure of vapor of liquid above the surface of liquid which is equilibrium with the liquid in a closed container at a constant temperature. This definition you already studied in lesson equilibrium of 11th class. Okay, it depends on the nature of liquid and temperature. If the temperature increases, then the vapor pressure also increases and set to at an equilibrium. Similarly, if you decrease the temperature in a closed container, then again the equilibrium will set up and vapor pressure decreases. Nature of the liquid means the gases which has, read the third point, liquids which has low intermolecular force of attraction between the particle has high vapor pressure in comparison to those liquids which has more intermolecular force. For example, water which has a strong hydrogen bonding will evaporate less in comparison to ammonia gas. Ammonia gas has low intermolecular hydrogen bonding, so it will evaporate faster than water. Similarly, carbon tetrachloride, chloroform, these liquids have very low force of attraction, so they evaporate readily. Perfume, when you apply perfume on your body, then it evaporates quickly, readily, because its intermolecular force of attraction is very less. Now the fourth point, that is vapor pressure of a liquid is constant at a constant temperature taken in a closed container. Fifth point, different liquids has different vapor pressure at a same temperature because their intermolecular force are different. The last point, when a non-volatile solute or salt is mixed in a pure liquid, then its vapor pressure always decreases due to the decrease in the surface area of the pure liquid, which is partially occupied by the solute particles. Finally, the rate of evaporation decreases, which is a surface phenomena. The last point is very important to understand. This evaporation is a surface phenomena, and when the surface area decreases, the rate of evaporation also decreases. Suppose you take 1 liter of water in an open plate and the same 1 liter of water in a glass. So you found that the water will evaporate faster from the surface of a plate because its surface is more. Similarly, when you dissolve some salt in the water, then its surface is occupied by the particle of the molecules of solute, and the rate of evaporation always decreases. It is the factor due to which the rest of the properties of the solution will change. Now we come to the next important topic, that is Raoult's law. Raoult's law, that is associated with two types of solution, means when a liquid is dissolved in liquid, then Raoult's law is different, and when a solid is dissolved in liquid, then Raoult's law is different. The first point, solution which has both volatile solute liquid and liquid, example ethanol, water, chloroform, acetone, benzene, toluene. In that situation the Raoult's law is different. And in second case, when solution which has volatile solvent solid but non-volatile solute solid, for example salt in water, urea in water, and sugar in water. So Raoult's law states that in case of one, for the first case, when liquid is dissolved in liquid, the Raoult's law states that for a solution of a volatile liquid, the partial vapor pressure of each component in the solution is directly proportional to its mole fraction. Quantitatively, it is given as below. Vapor pressure of pure liquid, that is PA. Remember that vapor pressure of a liquid is denoted by PA is equals to P naught A, that is its vapor pressure when it is 100% pure, multiplied by its mole fraction. Similarly, vapor pressure of pure liquid B is PB is equals to P naught B into XB. Let two liquids A and B has vapor pressure P naught A, P naught B. In pure state are mixed with each other and their mole fractions are XA and XB. In mixture, then total vapor pressure is, according to Raoult's law, the total vapor pressure is the vapor pressure of the individual component. Yani you have to add both the vapor pressure of both the components. That is P total is equals to PA plus PB. When you put the value of PA, that is P naught A into XA, and PB, that is P naught B into XB, then the total pressure equals to the second equation, or when you put the value of xa, that is mole fraction of a component, is equals to 1 minus xb, then you get finally the last equation. You can use either of the three formulas or equations to solve the numericals. Okay, so in the last point is written that the formula are used in various numericals. Try to solve the numericals. Now take the next slide, that is Raoult's law states that for a solution of a non-volatile liquid, that is the second point of the earlier slide, the partial vapor pressure of solvent volatile component in the solution is directly proportional to its mole fraction only. Non-volatile component like salt has no contribution in vapor pressure since it is non-volatile, so the only vapor pressure that is created on the surface of liquid is by the molecules of the solvent or liquid. The solid component does not play any role in the vapor pressure. Quantitatively or mathematically, it is written as P total is equals to P naught A into XA. Means the total pressure is only contribution of the solvent. There is no role of solid. When we carry out further calculation, that we get a final formula P naught A minus P solution. P naught A means vapor pressure of pure liquid. P naught A means vapor pressure of pure liquid, this term. This P naught A is vapor pressure of pure liquid minus P solution means vapor pressure of solution. Vapor pressure of solution, that is after the pressure when solid is dissolved in the liquid, upon P naught A, यानी कि vapor pressure of pure solvent, is equals to xb. xb, that is mole fraction of solid. So the relative lowering in vapor pressure of solution is directly proportional to the mole fraction of non-volatile solid. This is the statement of Raoult's law for the solid component dissolved in liquid. Clear? So there are two different statements, one for volatile component and one for non-volatile. So this is the statement for non-volatile component. Clear? Now Raoult's law as a special case of Henry law. Sometimes the question given in the board exam, that how can you say that Raoult's law is a special case of Henry law? So you have to write this statement: in both Raoult's law and Henry law, the partial pressure either of liquid and that of the gas is directly proportional to its mole fraction in solution. Only the proportionality constant are different, P naught A for Raoult's law and KH for Henry law. So based on the Raoult's law, the solution can be classified into two types. This is the very important question, that what are the two types of solutions based upon the Raoult's law. Let's consider the two types of solution. First is ideal and non-ideal solution. Read the difference, understand them. This is very important question given in the board exam. The solution which obey Raoult's law at all concentration is called ideal solution. Clear? Let's take the property of ideal solution one by one. The first is force of attraction between AA and BB is same as between AB. Clear? Means the force of attraction between solid particle and solvent particle is the same as that in between solid particle. The next is enthalpy change of mixing is 0. Means when you mix the two liquids, then there will be no change in temperature. The third point is VA plus VB, means the volume after mixing the two components is equal to the volume of the sum of two components initially. The next point is total vapor pressure is equals to the sum of the individual vapor pressure of both the components. The examples are benzene in toluene, chlorobenzene dissolved in bromobenzene, and hexane and heptane. The diagram is taken from NCERT book. Okay, you get straight lines in this graph. Now we come to the non-ideal solution, that is a solution that does not obey Raoult's law at all concentration. The second point is force of attraction between AA and BB is not same as in AB. Enthalpy change of mixing is not 0, means either heat is evolved or the temperature decreases when you mix the two liquid components. Total volume will also change. This is very important factor. When you mix the two solutions, then the volume is not equal to the total volume of the uh, two components, either the volume decreases or increases. Similarly, the total pressure will not equal to the sum of the individual pressure of the components. Raoult's law fail here. Examples are benzene dissolved in acetone, acetone dissolved in ethanol, and ethanol dissolved in water. And the diagram you can consult with the NCERT books. The graph has not a straight line, but it has curve. Now the non-ideal solution is again classified into two types. Okay, let's consider the two types of non-ideal solution. The first is the non-ideal solution which has positive deviation, and the non-ideal solution which has negative deviation. If the force of attraction between solute and solvent is less than between solute and solvent, then it is called positive deviation solution. In such case, enthalpy change of mixing is positive, means plus means endothermic. The temperature decreases when you mix the two such liquids with each other. Similarly, the volume also decreases. The volume increases, sorry, as a positive मतलब बढ़ जाएगा. The volume after mixing the two liquids will increases. For example, ethanol plus water, acetone plus ethanol. The pressure, total pressure is also more than the sum of the pressure of individual pressures. And you see the diagram that has increased curve. Then the solution, non-ideal solution with negative deviation, means the force of attraction between A and BB is more than between AB. The enthalpy of mixing changes negative, means heat is evolved during the mixing of the two components. Similarly, the volume, when you mix the two components, the volume decreases. P total also less than the, here the sign is wrongly placed. Actually, the total pressure is less than the sum of the individual pressure. And the diagram is taken from the book, that you get lower curve. So I think you read these types of solutions again after muting the sound, then you will also understand. So I think this is sufficient for this 10 a.m. work. Thanks for watching, and be prepared for the next colligative property at 11 a.m. Good day.